Hello, good morning everyone. Today inshallah we will continue on the topic of eigenvalues and eigenvectors. Hopefully today we will be able to finish this chapter. On next lecture, inshallah we will go through the inner cross product and the triple product, which is chapter 7. Today we will continue exploring the eigenvalue and the eigenvectors, and hopefully we will be able to finish this chapter today. I want you all to remember that the characteristic equation that we are using in order to get the eigenvalues is simply A minus alpha In equal to 0, where alpha is the values of the eigenvalues, I'm sorry. Okay, the characteristic polynomial, once you try to expand this equation, you will get a polynomial in general. This statement states that for any polynomial of degree n, you will have n roots. So it's actually connecting the polynomial theory with what are you going to face once you try to evaluate the values of lambda, which for the values of the eigenvalues. What I'm trying to say is, if I have a 2 by 2 matrix, I will end up having a quadratic equation that you will have a polynomial, okay, which once you put it equal to 0, it's going to be an equation with two values of alpha, even if they are real or complex. Also, if you have a 3 by 3 matrix, for example, you will end up having a cubic equation with all the theories that you can use in order to factorize a third degree polynomial in order to get the values, the eigenvalues that we will depend on later. Of course, he's stating that Am doesn't equal to 0 in order to keep the power or the degree of this polynomial. Also, all the coefficients belongs to C, which may be real if you are in the real dimension, or complex if you are dealing with complex coefficients or in the complex plan. K stands for the degree of this polynomial, and it will have n roots as I told you. Okay, I want to review with you two things, which is the algebraic multiplicity and the geometric multiplicity. First of all, for the algebraic multiplicity, it's simply the number of repetition of the roots of the characteristic equation. So once you try to solve this equation, you will get roots. This is what we understand. These roots are the eigenvalues. These eigenvalues may be distinct values or may be repeated values. If you have a repeated root, which means that you are solving x minus some value to the power of something. This is the number of repetition of this root. So the algebraic multiplicity, simply it's the number of repetition of any root from these eigenvalues. Okay, done. On the other hand, for the geometric multiplicity, I will go through it shortly, but just in case, it is the dimension of the eigenvector space, and we already defined that in the previous lecture. For example, if you have such an matrix, which is 3 by 3, now we understand it will have how many values of eigenvalues? 3. It will have 3, because you are dealing with a 3 by 3 matrix, okay? And it's really very simple to find. Of course, all you have to do is to, if you remember, to solve the system to solve the equation, which is simply, it's gonna be A minus alpha I equal to 0. So in this case, I am trying to factorize or to expand the equation, which is simply the determinant, which is 2, 0, 0, 0, 1, and 1, 0, 0, and 1. So once you substitute in this equation, you will end up having minus alpha, which equal to 0. Once you try to expand to get the determinant value, it's very, very simple. If you want to use Sarah's rule, it's also very, very, very easy. All you have to do is to multiply, as we know previously from the previous chapters. We will multiply the elements of the principal diagonal, which is gonna come up to easily into 2 minus alpha times 1 minus alpha to the power of 2 equal to 0. And this is really a very nice case in dealing with a third degree polynomial, because it's easy to factorize. Now, I will have the value of the first eigenvalue, which is 2, and for the second eigenvalue, I will have to put 1 minus alpha equal to 0. And this will develop alpha equal to positive 1. And it is repeated 2 times. So simply, what we are trying to say is that the algebraic multiplicity of the first eigenvalue is 1. But the algebraic multiplicity of 1 is going to be 2, because it's repeated 2 times. Of course, if you are trying to solve another matrix, let's say 4 by 4, and it's easy to factorize, and you have ended up having 2 minus alpha, 1 minus alpha to the power of 3. So the same way so the multiplicity of 1 is going to be 3, and so on. This is what's stated here. He is asking you to find the eigenvalues for the given matrix. All I have to do once more is to just subtract alpha from the principal diagonal. This is what this polynomial states for you. So simply I will get 2 minus x, 1 minus x, 1 minus x, and put the value of the determinant equal to 0 in order to get these roots. So you will end up having exactly the same equation. You will have the first bracket equal to 0, which will develop the first value of alpha, which is 2. Then you will put 1 minus x to the power of 2 equal to 0, and this is going to develop the second eigenvalue, which is repeated 2 times. Same. It's x equal to 2 and x equal to 1. Remark that the algebraic multiplicity of each root for number 2, the algebraic multiplicity equal to 1, we symbolize it usually by m of a, and then you put the value, the eigenvalue, and you seek the number of repetition of this root. Similar manner for 1, and it is repeated 2 times, so the algebraic multiplicity of 1, it's repeated 2 times. Okay, perfect. We can easily also find the eigenspace or the eigenvalues relative to each one of these eigenvectors. This is really very simple. We already did go through this in the previous lecture on a 2 by 2 matrix. Okay, just a second. Okay. Wait. I think I have some vacancy here somewhere. Not really sure. Just a second. أحمد هات ملايين. بس عشان امسح ده لأنه واضح إنه بيتبوظ. طيب. بص once more خلي بالك. This is the A matrix اللي احنا بنشتغل عليها. All I have to do is to just make a small substitution. Okay. So, in order to get, for example, the eigenvalues for alpha equal to, okay, let's start as this one for 2, for example. I will get back once more to the A matrix, subtracting the values of 2 from the principal diagonal. So I will end up having a system like, homogeneous system like this one, which is gonna be, okay, 2 minus 2, 1 minus 2, 1 minus 2. I'm just replacing the values of x by the eigenvalue. So simply, it's gonna be 2 minus 2, which is gonna be 0, and the other 2 elements is zeros. And for the second row, you will have 0, 1 minus 2, which is gonna be negative 1, and then you will have positive 1, same way like for the third row, you will have 0, 0, and then once more, 1 minus 2 it's gonna develop -1, okay, and it's equal to 0. I will need to reach the reduced echelon form in order to get the corresponding eigenvalue, which is very, very simple. All I have to do is to just replace these rows as we did previously. So I will have this row equal to zeros. I will replace the second row to be the first one, and while we are doing that, I will multiply by -1. So you will have 0, +1, -1, and 0. For the second row, for the third row, I will move it to the second one, and also I will multiply by negative, so it's gonna be like this. The second step is to reach as much as possible to a reduced echelon form. So all I have to do simply is to add the second row with the first row. So you will end up having a matrix on this form. Oh, this is the echelon form that we spoke about. This is double zeros, 1 and 0. And for the first row, it's gonna be 0, 1, 0, and 0. Now I can expand these values. Okay, so if I'm talking about the coordinates of the eigenvector to be A, B, C, since we are talking about a vector in 3D. So for the eigenvector U1, which consists of A, B, and C as a coordinates, this is gonna be A, this is B, and that's C, which is going to develop B equal to 0, C equal to 0. Taking these values and going back into U1, I will get the value of the first eigenvector, which is corresponding to 2, which is simply going to be U1 equal to A will remain the same, B and C equal to 0s. So this is the form that we are talking about. This is a general vector, which contains A belongs to R. So the span or the eigenspan for this eigenvector simply can be done by considering the vector which is 1, 0. We really did go through this through vector spaces plenty of times. Okay, so I'm having the main form that if you multiply by a number, you will generate this vector. Okay. From me solving this equation. Once more, Mr. Ahmed, and I started with the equation which states that A minus lambda I equals 0, okay? But on a matrix form. So you are trying to solve a homogeneous system which is simply A, once more, A minus alpha I equals 0, which is a homogeneous system, okay? This is why I've taken this matrix and I've replaced x by the values of the eigenvalue that you need to find the eigenvector corresponding to it. So I've replaced x by 2. Replacing x by 2, it means you will get the eigenvalue. The eigenvector corresponding to the eigenvalue which equal to 2. معايا مستر أحمد؟ Okay, done. يبقى أنا على طول أول ما عملت السبستيتيوشن اللي حضرتك شايفه بدأت أحاول أوصل لمين؟ Reduced echelon form. You are trying to solve for what? You are trying to solve for a vector. Vector in 3D which contains 3 components. Yes? First, second, third. Okay. Once you reach this equation, you will find that B equal to 0. C equal to 0. Taking these two values and you're trying to substitute back in the form of this vector which contains 3 components. Replacing B and C equal to 0s, you will end up having just only A. And the A belongs to the real number, to the set of real numbers. So I can take A as a common. I will have 1 double 0 stand for the eigenvector corresponding to what? 2. Exactly similar manners will be done, but using alpha equal 1. So once more, he's writing this a set, putting you that M2, which is the eigenvalue corresponding to alpha equal 2, it is the set of all vectors, which is going to be on the form ABC, that belongs to a column vector, such that the system that you can see now, it's a homogeneous system, which is, you have obtained it by just substituting by the value of 2 in the main matrix. Okay, done. Try to solve this system, you will end up, this homogeneous system, you will end up having this matrix. Okay, try to play with the row operations in order to reach a reduced echelon form. Done. Okay, the way you like it. Then you will end up having a general vector. The general vector contains A which belongs to R. I can simply take A as a common, and then I will get the span of this vector space, which is a column vector, stand for the eigenvalue. So, similar manner, okay, done. ده الفيكتور اللي انا بتكلم عليه والسبان بتاعه هيبقى 1 double 0 as I told you previously. Similar manner, if I want to use for alpha equal 1, same way like, I will make exactly the same substitution in the A matrix, but instead, I will have 2 minus 1, okay, then 1 minus 1, then in a similar manner, 1 minus 1. Doing so, you will end up having a system like this. This system implies that A equal to 0, B equal to 0, and C is your free variable. So, if you make this substitution, you will have A and C equal to zeros, B not equal to 0. So you will end up having the span which is 0, 1, and 0. Okay? معايا يا شباب؟ نفس الستبس، نفس السيكونس اللي احنا شرحناه المرة اللي فاتت on a 2 by 2 matrix. It's exactly similar. The main issue once you try to solve a 3 by 3 matrices is the main obstacle that you will end up having a cubic equation. If the matrix is nice, you will end up having a suitable, not a quadratic, a cubic equation that's easier on you to solve. Okay? Okay, done. يبقى انا كده جبت الايجن سبيس بتاع الفيكتور بتاعي. طبعا لاحظ ان الجيومتريك multiplicity stop. What we mean about geometric multiplicity? Geometric multiplicity, it is the dimension. Please. This chapter connects a lot of things at once. Your knowledge with vector spaces, the knowledge of a linear transform, as we will see shortly, and also all the knowledge that you know about eigenvalues and eigenvectors. All of them connected together. Okay? So, the geometric multiplicity, and we symbolize it by mg, stands for geometry, okay, or geometrical, okay, for 1, which is 1. Statement, another say, oh, this also statement or this remark, it's really very useful. What if I want to evaluate the eigenvalues corresponding to a unit matrix? Here's a remark about this situation in specific. He's telling you that in this statement and this remark that if we consider a matrix In, so I'm dealing with the unit matrix. Of course, all of you remember the unit matrix, which is a diagonal matrix with the principal diagonal equal to positive 1. So, if I try to find the eigenvalues corresponding to a unit matrix, what's gonna be? It's gonna be 1 minus alpha to the power of n. And the n stands for the rank of this identity matrix. Okay, simple. Okay, consider the matrix In. The characteristic polynomial of this matrix is simply gonna be 1 minus x to the power of n. It's a diagonal matrix, so if you try to get the determinant, all you have to do is to multiply the diagonal elements. And here the diagonal elements, all of them, is gonna be on the form 1 minus alpha or 1 minus x, whatever the symbol that you are dealing with. So, if I have a 2 by 2 I matrix, which is gonna be simply 1, 0, 0, and 1, and I'm trying to get the eigenvalues of this matrix, I will end up having a determinant on this form 1 minus alpha or x, whatever, equal to 1 minus alpha, and it's equal to 0. This is what the statement is telling you. You will end up having 1 minus alpha to the power of 2, which equal to 0. So the algebraic multiplicity will equal to the rank of the identity matrix. And if you are trying to get an eigenvector for this matrix, okay, you will end up having a zero vector for the eigenvalues. It's logic. لأنك simply, Mr. Yusuf, you will try to solve exactly the system minus alpha equal 1, minus alpha equal 1, and it's equal to 0, of course, times the values of alpha that you are trying to solve with. So you will end up having a 0 times x equals 0, which means that the eigenvector for the identity matrix, it can be any column vector from the same dimension. This is the statement here trying to show for you. But we're talking about a general I matrix, so it's to the power of n. So if it was 2 by 2, you will end up having 1 minus x to the power of 2. If it was 3 by 3, it's going to be 1 minus x to the power of 3, and so on. Okay, the statement said here, In has only the eigenvalue of 1. Logic. Okay, and the algebraic multiplicity will be n, also logic. It equal to the dimension of this eigenvalue. Okay, if I try to find the set for the eigenvectors corresponding to this value of the eigenvalue, I will end up solving the system. Once you try to solve this system, you will end up having 0 times the eigenvectors equal 0, corresponding to the eigenvalue equal 1. And this means that all the x column vectors from the same dimension could be an eigenvector. This is exactly what the statement states. Thus, the geometric multiplicity of 1 equal the dimension of m1, which is n. We conclude that each vector x belongs to the set of column matrices with x doesn't equal to 0 is an eigenvector of In corresponding to the eigenvalue equal to 1. It's a nice remark. Stated here in your slides, this statement, which states for this proposition, okay, but I think it's not written quite good. Okay, he's stating for you that let A be a square matrix. The following statements are equivalent. I don't think he means that. Okay, A is an invertible matrix. A hasn't the eigenvalue equal to 0. The constant term of the characteristic polynomial of A is not 0. I think it should be written like this. If A is an invertible square matrix, now A can invertible square matrix, this will imply of order n, this will imply the following statements are equivalent, just only these two statements. Because if you have an n by n matrix, you will end up having a polynomial or an equation with degree n. Degree n, it means it will have n roots, okay? It will be invertible if none of these eigenvalues equal to what? 0. And step number 2, okay, this is remark number 1, and also, which makes sense, if you are trying to solve a polynomial and the 0 is not one of its roots, you will have the final term. You will have the constant term for this equation. حضراتكم فاهمين بقول ايه؟ تعيد تاني. لو انا عندي matrix 2 by 2 مثلا, matrix 2 by 2 will develop a second degree equation. صح؟ second degree equation عشان الماتريكس 2 by 2 دي تبقى invertible, تعرف تجيب لها inverse, لازم ما يكونش الالفا واحد من الايجن فاليوز equal to 0. طيب كمان ملحوظه, هو امتى اصلا بيطلع لك واحد من الفاليوز equal to 0؟ لو كانت الايكويشن اللي انت بتحلها مثلا x سكوير minus 4x equal 0, يعني الكونستانت تيرم ده مش ماله؟ مش موجود. معايا يا شباب؟ كده كده تقدر تجيب واحد من الروتس equal كام؟ equal 0. يبقى لو الماتريكس بتاعتك اصلا invertible عشان عايز تجيب لها inverse, يبقى لازم تخلي بالك ان الالفا مش تساوي كام؟ مش تساوي 0. طيب معناها ايه ان الالفا مش تساوي 0؟ يعني البولينوميال اللي انت تفكها لازم يبقى فيها اللاست تيرم, الكونستانت تيرم, وبالتالي مش هتحصل على الالفا بتساوي كام؟ 0. فيبقى الستيتمنتس دي زي بعض. فاهمين قصدي ايه؟ اوكي؟ بجد فاهمين انا بقول ايه؟ مش واضح. اما يبقى عندي ماتريكس 2 باي 2 وعندي الفاليوز بتاعتها 2 3 4 and 5، لما باجي اقول ماينس الفا وبساوي ده بزيرو علشان بصول في الديترميننت، ده هيدي لك كوادراتيك ايكويشن. الكوادراتيك ايكويشن دي علشان تبقى انفرتبل ما ينفعش واحد من الفاليوز بتوعها يكون بكام؟ بزيرو. طيب امتى يبقى بزيرو؟ لو انت جيت فكيت دي لقيتها مثلا some number alpha square plus or minus some value في alpha equal 0، ده any value، خلي ده B خلي ده A، ده الشكل الوحيد اللي يديفلوب ان عندك روت بزيرو. ازاي هيجي لك روت بزيرو؟ لو هنا في نمبر مستحيل تجيب زيرو، مستحيل يبقى في روت بزيرو. فهمت؟ فلذلك الستيتمنت هنا بيقول لك لو ال A is invertible، يعني A دي ممكن ان انا اعمل لها inversion. اوكي. So in order in blah blah blah. The following statements are equivalent. مين اللي equivalent؟ The second statement which hasn't the eigenvalue equal to مين؟ to 0. عشان تبقى invertible ما ينفعش يكون لها eigenvalue بكام؟ بزيرو. واصلا لا يمكن هيطلع لها eigenvalue بزيرو، ده مع الستيتمنت الثاني، الاثنين زي بعض بالظبط. الستيتمنت الثاني بيقول ايه؟ The constant term of the characteristic، مين الكاركترستيك بولينوميال؟ ده اهي. ما ينفعش الكونستانت بتاعها يكون بكام؟ لانه لو بيساوي زيرو خلاص يبقى انت جبت الفا بزيرو. اوكي؟ ده المعنى بتاع الستيتمنتس. طيب انزل خلي بالك الديفينيشن ده احنا خدناه in the previous in the last lecture in linear transformation. كان بيقول ايه؟ كان بيقول let A و B matrices belongs to the square matrices. طيب we say that A and B are similar. امتى يكونوا similar؟ ال A وال B امتى يكونوا similar؟ خلي بالك if there is an invertible matrix اسمها مين؟ P such that P minus 1 AP will equal to B. يبقى انا لو عندي ماتريكس اسمها P هشوف ازاي بجيبها دلوقتي، طبعا related للايجن فيكتورز احنا شفنا المره اللي فاتت ازاي بجيبها اللي هي الاورثو نورماليزد موديل ماتريكس، او عموما الموديل ماتريكس اللي هي سكوير ماتريكس الكولمز بتوعها ار الايجن فيكتورز. اوكي this is the bottom line, but he is trying to introduce it for you by remembering first how matrices are similar. يبقى اذا انا عرفت ان لو عندي A و B وال A وال B دول two matrices ممكن يبقوا similar لو انا لقيت ماتريكس اسمها B، لو جيت اضرب B minus 1 في A في B خليتها بتساوي مين؟ ماتريكس. طيب بيقول if A و B belongs to square matrices are similar، لو هما الاثنين similar خلي بالك ايه الادفانتج اللي انا هاخده لو انا عرفت ان ال A وال B دول similar؟ ان then their characteristic polynomials are equal. يبقى لو عندي A و B similar to each other، يعني لو نجحت بالفعل اجيب ماتريكس لل A similar ليها اسمها B، ايه الادفانتج اللي انا هاخده؟ ان الكاركترستيك ايكويشن بتاع both of them they are the same. طب هو الكاركترستيك ايكويشن دي انا بجيبها منين؟ remember من الايجن فاليوز، ده معناه الايجن فاليوز بتاعتهم مالها؟ the same. if A و B n are similar then their characteristic polynomials are equal. Okay, this implies that A and B have the same eigen, exactly what I've said to you. Okay, with same algebraic multiplications, يعني أو multiplicities, which means نفس identical, two equations identical to each other in every value. ده كل ده entrance علشان أقدر أوصل لdiagonizable matrices. المرة اللي فاتت أنا وريتك على طول وبسرعة الستبس التكنيكال عشان اقدر اجيب ايجن مين؟ فاليوز، بعدين اجيب منهم مين؟ ايجن فيكتورز، بعدين اديفلوب الماتريكس اللي اسمها ايه دلوقتي هنشوفها؟ بي، اللي هي لو جبت لها انفرس وضربتها في الاي از ساندوتش زي ما انت شايف كده هيديفلوب سيميلار ماتريكس. ذيس از بوتوم لاين. يعني مين بقى السيميلار ماتريكس دي؟ It's gonna be a diagonizable matrix. ومش اي diagonizable انا اسف diagonal matrix، مش هيبقى اي diagonal matrix، لا هيبقى diagonal matrix والاليمنتس بتوع الدايجونال هم مين؟ الايجن فاليوز. ده اللي هو بيحاول تو انتروديوس ات فور يو، بس ستيب باي ستيب بيزد على الثيوريز اللي انت اوريدي عارفها in the back of your mind. اوكي؟ done. Once more, what's an endomorphism? What's an endomorphism? I've introduced it to you in the previous session. اوكي ده اندومورفيزم. شايف الحركه دي شديده. بيقول let E be a vector space over K. يبقى انا عارف ان ال E ده vector space over K. يعني ايه K؟ يعني ايه K؟ السيت اوف ريال اور كومبلكس عشان يبقى بيتكلم من ايه؟ جنرال. بيقول we call endomorphism. مين الاندومورفيزم؟ طبعا هو ده مش موجود، الستيتمنت ده مش موجود اكزاكتلي طبعا للجنرال ارينجمنت بتاع السلايدز بتاعنا، بس انا حبيت تو امبيدد هير عشان بس تو ريمبر يعني ايه اندومورفيزم. تاني وانس مور اهي تاني اهي. اوكي الاندومورفيزم it means that you do an identity linear transform. شو بقى خلي بالك انا دلوقتي هبدا لينك ايه؟ الليله كلها مع بعضها، كله هيركب مع بعضه. يبقى انا لما بتكلم على endomorphism it means that you are making a linear transform from E into E. معايا مسيو برايم؟ اوكي. Transform of E to E. اوكي done. كمل. بيقول let F be an endomorphism of a vector space E such that the dimension of E is finite. يعني الدايمنشن بتاع ال E ممكن يبقى R3 R4 R2 whatever. بيقول and let بيتا. مين بيتا دي كمان تجري في الوسط كده؟ B an arbitrary basis for E. any basis for E. وانت عارف قبل كده ان الفيكتور سبيسز مش شرط ان يبقى لها one basis. لا ده ممكن يبقى لها multiple مين؟ basis. ده اللي احنا خدناه في اللينير ترانسفورميشن by the end of the previous chapter. ده الراجل كان بيقول علينا نعمل كباري. اوكي done. بيقول we call characteristic polynomial of F. خلي بالك انا دلوقتي هبدا اتكلم على condition مهم جدا ان انا هبدا اتكلم على الكاركترستيك ايكويشن بتاعه الفيزل اللي بتنقل من فيكتور سبيس سب فيكتور سبيس into another sub vector space. فانكشن المسؤول عن ده. اوكي؟ يبقى تاني نعيد تاني الكلام ده. خلي بالك ان الديفينيشنز اللي موجوده في السلايدز مش مجرد انك تريد ات. لازم تريد ات in focus. So once more, let F be an endomorphism. What do we mean about endomorphism? Written for. ان انا بعمل identity transform. اوكي done. بيكمل وبيقول of a vector space اسمه E. يبقى انا بنقل من E into E. Done. Such that the dimension of E is finite. So it's a limited one. R2, R3 or whatever. And let beta one of the bases in E. واحدة من البيزس اللي موجودة فين؟ في ال E. Okay. We call characteristic polynomial of F. الفيزل اللي انا بنقل بيه. الطريقة اللي انا بموف بيها from E into E. Okay. Of F to the characteristic polynomial of the matrix. مين الماتريكس دي؟ ها؟ يا اسطى مين الماتريكس دي؟ MF such that from B to B. مين الماتريكس دي؟ دي الماتريكس اللي هي بقول عليها الكوردينيت. What? اوكي الماتريكس of coordinate sequences اللي هي responsible about انك to move from a linear transform into the identity linear transform. دي الماتريكس اللي انا بتكلم عنها. اوكي؟
فكرش فيها معايا.
بيقول just live in a second. خليني اقول بس
عشان تجيب درجة عالية في الشغل.
Okay. I will read it once more. اوكي يا شباب. تاني once more. ارجوك ركز معايا. بيقول let F be an endomorphism of vector space E such that the dimension of E is finite and let beta an arbitrary basis for E. الكاركترستيك polynomial of F يعني الكاركترستيك polynomial بتاعت الفيزل اللي بنقل بيه او الفانكشن اللي بتنقل من E into E. Also the characteristic polynomial which is the matrix of coordinate sequence اللي انا بفورمت نتيجه اللينير ترانسفورم بتاعي. بيقول لك F be an endomorphism of a vector space E such that the dimension of E is finite. Let beta an arbitrary basis for E. لو البيتا arbitrary basis for E وانا عندي دي الترانسفورم بتاعي U is the eigenvector of F. خلي بالك لو سمحت ده ستيتمنت ده مهم جدا. لو اليو is an eigenvector of F هيبقى if and only if يعني ده يحصل بس. خلي بالك if the matrix X اللي هي الايجن فيكتور يعني which belongs to a column matrix يعني ايجن فيكتور يعني انسى الحته دي اسمها ايجن فيكتور بيقول whose column is the coordinate sequence of U يعني هيبقى الايجن فيكتور هو اللي الكوردينتس بتاعته خلي بالك of U relative to basis مين؟ بيتا. So he's trying to connect الايجن فيكتورز مع الكوردينيت سيكونس بتاعت اي فيكتور اسمه يو ريلاتيف للبيزس بتاعت الفيكتور سبيس اللي انت بتنقل منه. كلام محتاج انك تبقى فاهمه كويس جدا، مجمع اللي فات كله تفهمه سنه بسنه. انا فضلت طبعا هنا برضو، طب خليني اخلص دي واقول لك انا هكتبها لك باسلوب تاني. بيقول U is an eigenvector of F if and only F. يبقى اذا اليو ده ممكن يبقى مين؟ eigenvector بتاع الفانكشن اللي اسمها مين؟ F اللي بتنقل بين الاثنين. if and only if لو هو بيقول ده ماتريكس خلاص لو هو الايجنفكتور اللي العمود بتاعه هو الكوردينيت سيكونس بتاعت اليو بس ريلاتيف للبيزس اللي اسمها مين؟ اللي اسمها بي. يبقى خلي بالك انا كده جبت الايجن فيكتور اللي هو اسمه يو بتاع الاف واللي هو الكوردينيت سيكونس بتاع مين؟ الاي. طيب جميل جدا. نقراها تاني بشكل ألذ او اسهل شويه في الفهم. بيقول ده coordinate sequence of u يعني الكوردينيت سيكونس بتاع اليو يعني بجيبه ازاي الاول؟ يعني ايه coordinate sequences؟ لسه في حاجه يعني ايه coordinate
حاسس الكلام كتير قوي في الكورس.
يعني ايه coordinate sequence؟ ارجع تاني للفكره بتاعت اللينير كومباينيشن. اي فيكتور اسمه يو انا اقدر اخلقه من بيزس. بخلقه ازاي؟ بمسك يو 1 واضربه في الفا 1 زائد يو 2 واضربه في الفا 2 زائد يو 3. ام سوري ان انا كررت كلمه يو اكتر من مره. خلينا اقول في. بقول ان الفيكتور اللي اسمه يو بيساوي الفا 1 في في بلاش الفا. خليني اخليها ال. فبقول ان الفيكتور اللي اسمه يو ده بيساوي L1 في V1 زائد L2 في V2 زائد L3 في V3. مين ال L1 وال L2 وال L3؟ الكوف اللي هم الكوردينيتس. تمام كده؟ نعيد تاني الكلمتين.